Hello, here is your walkthrough for Lab 10A on Goodness of It. So make sure you download both the data file and your lab, and let's get into it. So by way of review, let's look at the tests we've done so far. We've done a test of a single proportion. That was our first test. Then this was Lab 9A and Lab 9B. We did a test of difference of proportions. So two proportions. We want to know if P1 minus P2 is equal to 0. Okay, so that was Lab 9A and Lab 9B. In this test, we're going to be looking at test of many proportions. So it's really helpful to distinguish these tests. This is really our third test we're doing in this class. And with this test, instead of having one or two, P1, P2, we have three or more proportions. And so this changes how we're going to test it. And so the test we use when we have many proportions, it's called the goodness of fit. It uses a different distribution. Okay, there's some review and some context. So let's look at some distributions. We've talked about the normal distribution so far. Here's the standard normal distribution. Normal 0 means standard deviation 1. We call that Z. That distribution looks something like this. That's our standard Z distribution. Now, let's consider, what if we square this Z distribution? What if we take our values, every value of X, and square it? What do you think will happen? And since I know a little bit about math, if you take a negative number times a negative number, that gives you a positive. So all these negative numbers are going to get flipped over here. They're going to be all positive. And I'm going to guess that 0 will be the most common value still. Is that the case? Okay, that's just some guesses. Now here's a bit of code that actually will plot the z-squared distribution if we take that value and square it. And sure enough, it looks like this. There's our z-squared distribution. So that's a new distribution. Not that we're going to use this distribution per se. What we're going to do is we're going to add up z distributions to get what's called a chi-squared distribution. So the chi-squared distribution is a distribution with only one parameter k. And what the chi-squared says is, hey, whatever number my k is, I'm going to add up that many z squared. And that's going to be what we call the chi-squared distribution. Chi-squared. Occasionally I slip and say chi because that's what it looks like, or chi, but it's chi-squared. So unlike the normal distribution, which has the mean and standard deviation put into there, the chi-squared only has one, degrees of freedom, or df. So the way we can plot the chi-squared is using some code I have here. You don't have to pay much attention other than we're using a function d chi-squared that plots it for a given degrees of freedom. So there's the 1 degree of freedom. That means we just add up 1 z squared, which is what we plotted earlier. So that's the chi-squared with 1 degrees of freedom. That's just a plot. And we're familiarizing ourselves with what these plots are. So here's the chi-squared distribution for 1, 2, 4, 6, and 8 degrees of freedom. Let's look at what's happening here. Ooh, is that not beautiful? So yellow is 1, red is 2, purple is 4, blue is 6, and green is 8. You see what's happening? The more we add these up, the more we get a hump that's further out. So here's the chi-squared with 10 degrees of freedom. Here's what it looks like. And now we plotted the whole thing so it kind of fills the graph. And let's say, hey, what seems to be the most common value of this distribution? Right now, we're just studying aspects of it. What appears to be like the most common value? Not going to let me draw. There we go. Is that what I want? Yeah, there we go. Most common value. It looks like something about 9. You see how 9 is like the peak? I'll say 9. But actually, if we want to look at what the average is, or the mean of my chi-square distribution, notice that there's a right skew on this distribution. Chi-squareds will be right skewed, meaning if I want to find out where half the data is, I want half the data to be on the right, half to be on the left. It turns out for the chi-square distribution, it's always the degrees of freedom. So 10 is going to be the mean. So the mean is always equal to the degrees of freedom. That's just a side fact. Okay. Mostly now you know kind of where the chi-squared comes from. Not that any of it matters for using it so much as I want you to be able to find upper and lower tail probabilities accurately. So we're going to do the same thing we did in lab 6 with normal distributions. We're going to start finding upper and lower tail probabilities of our chi-squared. So here's a plot. Here's our chi-squared with, it looks like, 3 degrees of freedom. And I've just highlighted the area between 0 and 6 for you to see, hey, what's that area going to be? Okay, so to find that area, we're going to use a function called, instead of p norm, we're going to do p chi-squared. And the first number that goes in is our quantile, and the second number will be our degrees of freedom. So we can find out that area, p chi-squared. Uh-oh, I don't know what that means. Q equals 6, and the degrees of freedom was 3. Meaning we plot our 3 degree of freedom chi-squared. I'm finding the area of everything 6 and below. That's about 88%. Which you can see from this, it looks like about 88% of the total area under the curve. So now your job is to find the lower tail probability of the chi-squared of 4 degrees of freedom with everything below 4.3. So if you want, you could plot that just to kind of see what I'm saying. We got a chi-squared with 4 degrees of freedom. Now I want to know everything below 4.3. So that's the area I'm looking for. So to calculate that, we're going to use p chi-squared. P chi-squared says everything below our quantile Q, 4.3. There's our quantile, 4.3. And the shape of my graph is determined by my degrees of freedom, which was, I think, 4. Yeah, 4 degrees of freedom. Okay, so we'll have to also change this to 4. So there's my answer for my area that I highlighted here. So how about you do 5 on your own and then pause the video before seeing my solution. Yeah, lower tail probability of everything below 5.1 having 5 degrees of freedom. Okay, that's how we do lower tail probabilities. Next, let's cover some upper tails. How do we do an upper tail probability? Here's everything below 4.3. Sorry, everything above 4.3 with 4 degrees of freedom. How do we find that area? Well, the whole area, since it is a distribution, all these distributions have the property that the total area, what is that? Total area is always going to be 1. So if I take 1 minus, say, the pink area, that'll give me the red area. 1 minus pink area, that'll equal the red area. So that's that's where we go in finding our lower tails. So we're basically going to say 1 minus the lower tail. Everything below 4.3, and we're looking at the graph of 4 degrees of freedom. There we go. So that'll be our upper tail area there. Okay, see if you can do 7, 8 on your own, and I'll give my solutions here for you to check. But please, now that you have the ability to do this on your own, start practicing. So looking at the upper tail, I could say this. Or I think I might have shown some of this. You can always do the same thing here. And if you say lower tail equals false, that's the same thing as finding the upper tail. It's another way to get the same thing. Although I prefer doing this. 1 minus, that means I'm doing the upper tail. I want you to get you to be doing these quick because we're going to be using these in context of a larger hypothesis test. Okay, so now we're ready to do our hypothesis test for the chi-squared statistic. Okay, so if we have many proportions, at least more than 2, 3 or more, we're going to want to use the chi-squared test, which uses a particular statistic that takes the observed value minus the expected value, number of counts over the expected number of counts for any category. And to put this in context, I have to look at our data. Okay, here's some data. We got a jury. The jury was selected and there was 26 black people, 25 Hispanic, 19 other, and 205 white. We want to know, is this jury representative of the actual population in the area? So I'm just going to add the sum to this jury so I can see, oh yeah, there was 270 people total on my table. And now let's do some studying. What is the population of the area actually? So the population, this code says, hey, 7% are black, 12% Hispanic, 9% other, 21 white. That accounts for all the population. Is this jury here representative of my population? So let's calculate what we would expect to see if it was representative, if it was proportional. So if there was 275 people in the jury, we would expect to see exactly 7% black, right? And if there's 275 people in the jury, we would expect to see exactly 12% Hispanic. And so that's what we would expect to see. Let's see if we can find out what the remaining proportions are for other and white. Oops, 275. Expect to see 24% other. And 72% white. Those are the expected counts that we would see. And you can actually do this all at once by just taking this table here, population times 275. That's what we did, but I'm going to do it all at once now. So here are expected counts. I'll call that EXP for expected counts. Maybe I'll use that later. Let's see. Those are expected counts. What we observed actually was jury. So I'm going to say my observed I'm just wanting to see all this data here at once. Okay, so what we observed was this data: 26 black, 25 Hispanic, 19 other, 205 white. And we expect to see 19 black, 33 Hispanic, 24 other, and 198 white. So the question is now, are these two things different or the same? If they're the same, that means it's representative and there's no bias. If they're different, statistically different, that means not representative. That means there was evidence of bias. Okay, so we're going to test this. The goodness of fit test can show us this. So to make our test, we want to set up our hypothesis. The null hypothesis says there is no difference between what the difference you see in random. I could say any difference you see in jury and expected counts are due to chance. So in other words, we would say the observed counts equals expected counts. Really, they're the same. Okay. And then the alternative would say, nope, the observed counts are not the same as the expected counts. I'm going to use those terms, observed and expected, pretty consistently. Okay, so here, no, any difference you see, it was due to something else going on. So there was bias. And now we have a test. We're going to build up a test that can do that. So, oh, I already did the same thing before. So here it is again for you. We got our observed and expected counts. And so what we do with all this information is we put together our chi-squared statistic. For each category, we take the observed value minus the expected and divide it by 1. We square it and then divide by 1. So let's find that out. Here's your data for you. We're going to take the observed, which is 26, minus the expected, 19.25, square it. This is for the white. And we're going to divide by the expected, 19.25. So that was for the white category. That was all this mess here. Now we got to do it for the black category. So for the blacks, we say there were 30 observed minus expected. Observed. There was 25 observed minus 33 expected. Square that and divide by the number expected. Observed minus expected divided by expected. And now we'll proceed to the other category. There was 19 observed minus 24.75 expected. Square it divided by 19 expected. That's our 4 categories. And then our last category is white. We observed 205 minus 198 expected, square it divided by 198 expected. And the last category would be 0 if we did it, because they're both 75. So that'll be our chi-squared statistic. This is the number that falls on our distribution. We draw our distribution, 6. Wherever 6 is on our distribution, that's what our data tells us. So I just want to show you another way to do this if you want to save time. If you have it all saved like this, we can say observed minus expected, square it and divide by expected. This is optional, but if you want to do it this way, this tells us the difference squared divided by the expected for all the categories. And then if we sum them up, this will be identical to what we just found. If I did it right. So I'm seeing a difference. So let me check my math here. Maybe you already found that I made an error. 25 minus 33 by 38, 19 by 25. Oh, here we go. I should say 24.75 here. Expected is 24.75. 5 expected. Okay, run that again. Okay, now they're the same. Good. So now they're the same. You can see this is a little more accurate if I do it this way. So that's my chi-square distribution. And so now we just want to make sure, do our conditions satisfy the assumptions for using this test? We got to say, hey, was every count in our table independent of all the other counts? And if we were random sampling, yes, they should be. And then we want to have at least 5 expected counts for our sample size to make sure we're looking at something that's big enough. So our expected counts, at least 5. Boom, 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 boom. These are expected counts here. And yes, they're all at least 5. Yes. All at least 5. Good. So if that is the case, we have a situation where that statistic, that value we found here, 5.889, should come from a distribution that was a chi-squared with k minus 1 degrees of freedom, where k is the number of categories. So I had 4 categories here, 1, 2, 3, 4. This follows a chi-squared distribution of I'm going to draw my distribution here now. It's 5.89. This will have a degrees of freedom of 4 minus 1, since there was 4 categories. So now I want to find out what's the chance of observing something more extreme than the data I observed. And sing yourself a song. P-value, chance we've observed our data if the null has occurred. So given our assumption that they're equal, it should follow this distribution. This equates to finding the upper tail probability. 1 minus p chi-squared. Oh, I don't know why it's doing that. Squared of 5.89 is what we observed. The degrees of freedom was the number of categories minus 1. So there we go. So we got a p-value of 0.117, which is greater than our usual cutoff of 0.05. So now we can sing p-value getting too big. No evidence for alternative. So we can say, since, set this up here, since p is greater than 105, we don't have compelling evidence for what is the alternative state. Alternative said there was bias. So we can say we don't have evidence for bias, at least compelling evidence. So when we look at those samples, what we observed and expected, the difference that we observe are apparently due to chance from our test. So that's what we found. Okay, so I'm going to clear this all. And now is your chance to practice 2 examples. I'm going to maybe set up the barking deer example for you guys together, and then we can check it. But actually, with both of these examples, I have a bit of code here that you can use to check it. R is fancy in that it has code often to do all your hypothesis tests by themselves. So after you do the open source textbook example, you can check it. Actually, I'll do the textbook example. I'll do this one, but you should really do it by yourself before looking at me. This is only in case you need it. So please pause the video, work on it yourself, and then if need be, you can check the rest of the video by seeing my work here. the difference. Okay, here are my hypothesis. We're measuring professors' predictions versus the students, what they actually said they bought. And so let's put this into two tables. This prediction, I'm going to say this is what we expect. So this is going to be 60%, 25%, and 15% for the three categories. And I'm going to multiply this by 126 because there's 126 students total. So this is what he expects to find. 60% of 126 is 75.6 students purchasing hard copies. And I'll make this clear. I can say names of expect, and I can say text, print, online, I should say. This just makes my life easier. I can see what I'm talking about. So here's the expected counts. 75.6 for hard copy, 31.5 for print, and check myself. Should get 126. I did that right. Yes, okay. That's just a check. This is what I would expect to find. I'm just going to use that same bit of code for observed, because observed, the numbers are just given. 71, 30, 25. So there's my numbers for observed and expected. So we have to set these up so that they're actual counts. When we use our chi-squared statistic, these are observed and expected counts. So back to the open source textbook, I have my observed and expected counts, and my null hypothesis says they're the same. Let's just look. Observed and expected, they look the same. To me, they look very, very similar. I'm saying we got a pretty good prediction. That's just my guess. So B already answered. That's my expected value. Okay. And now C, my expected counts. Now C is, do we satisfy the conditions for the chi-squared? I'm going to say yes, because my expected counts, at least 10. And then for D, let's find out what my chi-squared statistic is. This is going to be the sum of observed minus expected, square it, square that thing, divided by expected, just like that. I want to put this all separated by parentheses. So if you misplace a parentheses, you're going to get something totally different. Like if I accidentally put a parentheses here instead, it's not going to work. Okay. Yep. So what this tells me is I got my distribution. The degrees of freedom are the number of categories minus 1, so 2 degrees of freedom, and I observed a value of 0.2.32. Okay, so to find my p-value, I'm going to do 1 minus p chi-squared of what I observed. Just going to copy that. Okay, p-value. Okay. Now we sing the song, p-value getting too big. We do not have evidence for alternative. And then you can check it here. You should see I got the same chi-squared value, the same p-value here, and then the degrees of freedom was 2. Okay, so that's a work through example. You can check your work. And now it's kind of up to you to practice with the barking deer. All right. Good luck on the homework, and we'll see you in class.